So rotation in the flow has significant mathematical consequences, and so it has its own name, and it's called vorticity. So vorticity is a property of a flow, not of a fluid. A fluid flow can have vorticity, and vorticity is a measure of the local rotation in the flow. So let's imagine that we have our packet here, and it's rotating. In case we've drawn it as rotating counterclockwise. And so B has lifted up and D has shifted over as this box rotates. It may also be sliding along, but we're not concerned with that. It's rotating. So what causes that rotation? Well, this rotation, this lifting up of B relative to A, is caused because, obviously, the velocity in the y direction, so this would be your x direction and this would be your y direction, the velocity in the y direction, it must be greater here than it is here. So A is not moving upward as fast as B is moving upward, which means dv dx is greater than 0 to cause this counterclockwise rotation. So dv dx is greater than 0 is going to lead to that counterclockwise rotation of the box along this side. This side, the D point has moved less, is moved to the negative x direction relative to the A point. So that's going to be governed by the u velocity. So if du dy is less than 0, that is if the velocity in u is smaller up here at D than it is here at bottom, that's going to cause A to advance faster than D, or D to move backwards relative to A. So that's going to be du dy is less than 0. So the two factors that contribute to this rotation in two dimensions are a positive dv dx and a negative du dy. That's going to cause the box to rotate. If we actually try to look at the angular velocity around the point A, we can calculate sort of what that looks like. So there's your change in velocity of A relative to B. So it's changed by some amount. This v upward velocity has changed relative to this upward velocity, causing this to start to rotate with some omega a b angular velocity. And this distance, of course, is your delta x. So that is going to cause a rotation. If this B is moving upward more quickly than this A, it's going to rotate it counterclockwise. And we can mathematically calculate the amount of that angular rotation. So that's going to be our angular velocity. And we have the delta V divided by 2 pi delta x. Because, of course, that's 2 pi delta x is the circumference of the circle. If the thing were to go all the way around in a circle, delta x is simply the radius of the circle. 2 pi delta x gives me the perimeter of the circle, or the circumference of the circle. And therefore, if I take the delta v, the amount it moves per second, and I divide that by the total distance, and I multiply that by 2 pi, that's going to give me radians per second as a amount of rotation that's caused by this change. All right, so I can do the same thing for the D point. So again, I draw my picture. I have A, I have D. Now what's causing the rotational motion is this negative delta U, and and of course this is delta Y. So once again, I can calculate the angular velocity AD is equal to negative delta U over 2 pi delta Y times 2 pi. So that's also going to give me radians per second. And I've used the not negative sign here because that's going to give me a positive number for the same direction of rotation as the other one. So they're both going to be positive when they're rotating counterclockwise, and that's consistent with the right-hand rule. So my counterclockwise rotation gives me an upward thumb, and that causes me to have a positive number. All right, so that's how we're going to calculate this mathematically speaking. So we're going to put that into a average formula. So we're going to say, okay, that's the angular momentum around point A from B. This is the angular momentum around point A from D. So we're going to put those together, and we're going to say that the angular momentum, the angular velocity of this packet of fluid is 1/2 times the average of times those two things added together. So we have delta V over delta X, and then we have delta U, remembering that delta U is negative for it to be adding here. So So there's our formula for the total angular velocity of the packet. It's kind of an average angular velocity based on the motion of A and B and the motion of D and A, those both sides being averaged together. If I let this whole thing, delta x equals delta y, and they both go to 0, of course I get the differential form of this, and we call that the z angular momentum. So it's 1/2 dv dx minus du dy. So that is my z angular momentum for this box in the limit. So that's now the z angular momentum. I'm sorry, I keep saying momentum. It's z angular velocity. This is angular velocity at a point in the flow, because I've let delta x and delta y go to 0. So at any point in the flow, I can calculate this angular velocity at a point in the flow. So that is given a special name. As I said, it's referred to as, it's indicated by the vorticity, and we get rid of the 1/2. So we say that vorticity in the z direction is equal to this. So we get rid of the 1/2 just for this because it's annoying. So we just say this is a measure now of the angular velocity or the rotational velocity in that flow. And so if we want to represent that purely mathematically, we can say that the z component of the vorticity is equal to del cross u. So this is that's the cross product of the gradient with the velocity vector. So sorry, that's just the v vector. That's the whole vector. So we just say that the vorticity vector is del cross u, and this is a cross product. So this vorticity term allows us to get a mathematical representation of how much the flow is spinning. Positive vorticity means it's spinning, counterclockwise. Negative vorticity is spinning clockwise, and zero vorticity means the flow is not spinning. So certain flows have zero vorticity, and it turns out those flows are a special class of flows that we can study. Sometimes it should be noted that people use different symbols for vorticity. One of the more common ones is omega, so that's often used for vorticity as well. We used omega for angular velocity, so we used it here, so I didn't want to reuse it here. So I'm using zeta here as my vorticity symbol, but different books will use different symbols. But either way, that's your definition of vorticity, and next class we'll start looking at how you calculate that.